I'd like to welcome you to the Bristol Community College Environmental Technology Laboratory. In today's activity, what we're going to be dealing with is groundwater. And since groundwater makes up about half of the drinking water in the United States, it's very important that we have a good understanding of the groundwater and the systems that are involved with it. And so today we're going to be using an awesome piece of equipment called a groundwater simulator. And with this device, we're going to be doing several activities that are dealing with understanding of how water moves through the ground. To begin, we're going to go through the setup of the instrument. And notice there are various valves in the back of the device. And what we're going to be doing is make sure the proper ones are open and closed. In order to fill the simulator, we want to make sure that the outlet valve is closed. We also want to make sure that the valve that's leading to the sand, the actual aquifers, is also closed. But we want to open the other valves for the time being so that water can go in there and fill up the unit. So what we're going to do is attach this hose. It's good to do this next to a sink. And we're going to start to fill the unit. And we're going to fill it up to this water level right here. Once the water starts to come up, it's going to start emptying into the aquifer and starting to fill up the simulator. And so we'll wait for that. As that goes up, it'll take a little while for the sand and everything to fill up with water. So now you can see the water is emptying into here. This is porous, so the water is now going into the simulator. And if you can see it, you can see the water rising in the wells. Hey, once you can see that the water level has risen in here, and you can see the wells are pretty full, you want to lower the water level back to the level that's marked on the system. And so to do that, we'll just open up that valve in the back and just drain some of the water out. Okay. Now we want to fill up the pump. And this is basically an aquarium type pump, and this is going to provide the recharge water for our aquifer. So we want to fill up that container. There's 2 chambers in there. Want to make sure they're both full. And we're going to plug in the pump. And now what we have to do is get the water level to rise so that it comes up and fills the pump. So what we're basically having to do is try and get the air out of that line. So if you push that over to the right, and just do a few see, water levels coming up. Now you can see the water start to spill into the aquifer. And then we can actually control the flow two ways by moving this back and forth, and also by moving this device, which opens and closes the space. Right there. If you have it too much, you can see how it'll overflow. So we can reduce the flow. So if it's all the way over to the left, you get the maximum flow. Over to the right, you get the minimum flow. And this is going to control the level of water in the wells, because this is the recharge area. And so there are two parts on the aquifer. This is the area of recharge, and this is the stream. This is the area of discharge. We can control the level in the stream by adjusting this valve. And you just have to play with it to get it to the point where it becomes stable. And then this valve can control the water level in the lake. And that depends on the water level in the wells. Now, one of the things that we can show is we can use dye in here to show the level of the water in the wells. And this simulator actually has three types of aquifers. We have an unconfined aquifer. An unconfined aquifer is an aquifer that has a water table. And so the water table can rise and fall. We'll look at that in a moment. A confined aquifer is one that's confined on the top and the bottom, so that the aquifer area is always full and it's pressurized. And so then we have also another type of confined aquifer. This is a bedrock aquifer. And this is an aquifer that's right in solid rock, like granite or volcanic rock. And so where the water is, rather than in the groundwater here, the water is moving through the sand grains. In this confined aquifer, which is a bedrock aquifer, the water actually moves through cracks in the rock. So there's bigger cracks, bigger spaces that fill the area. What I'm going to do now is to put in a little bit of dye at the top of each well so that we can see the level of the water in the wells. I'm not going to put the water in these for a moment because I'll be talking about these two later. But here you can see where the water level is in these wells. And now you can also see that the water level in the lake has risen. We can adjust that. And if you watch, that can also adjust the level of water in some of the aquifers, in some of the wells. So we'll leave some of the water in there. Okay, one of the first things we're going to do is get an idea of what is the direction of flow in groundwater, which is an important thing when we're looking at an aquifer, and a lot of things that we do, what we're going to plan, how we're going to work with the land that's around an aquifer, is understanding the way that the water flows. And water flows in an aquifer by gravity. So what we will look at, we'll use GIMP. I don't know if people used to go to camp and you used to make a lot of things out of GIMP. This is just your simple piece of GIMP and some tape. And so we're going to first look at the water levels in the unconfined aquifer. And the wells that deal with the water in the unconfined aquifer are wells 3, wells 4, and wells 5. And so I'm going to put a piece of tape to hold the GIMP here right at well 3. So we can see it right at the level. And then we're going to follow the contour of wells 4 and 5. So you can see here's the level of well 4, here's the level of well 5. So if we put that right there. So we can see, following the lines, that the well is higher here and lower here. That means that by gravity, the water is going to flow from a higher to a lower area, so the water is flowing in this direction. An interesting thing also is if we look at this line, we also see that the water in the lake is right about at the center of that. And the reason for that is many lakes are what's known as spring-fed lakes. And so the water is actually coming from the aquifer into the lake. So this is actually the water table. So this line is showing the water table in that aquifer. And it passes right through the center of this lake. Right here, because this lake is being fed by the water from the aquifer. Now another measure of the slope of this, the slope of the line that looks at how the water table is going, is known as the hydraulic gradient. And so the hydraulic gradient, just like a gradient when you look at rise over run on a graph, that's the same here. We're going to look at the rise, or the fall of the water level from this height, from this location to this location, and then the distance between the wells. So we would just put this across and measure the distance from this well, center of this well, to the center of this well, and get that measurement. And then from here we would also get a measurement of the distance from that line up to the top of the well. And then we would do the calculation where we have y2 minus y1 over x2 minus x1 to give us the slope of the line. And that's the hydraulic gradient. So that's one of the things that we can do with this well, which is a hydrological parameter that's of concern. Now, another thing that we'll want to do is measure how fast is the water traveling through the aquifer. So what we can do is measure a couple of points. Right here, say from the start of this well to this well here is about 30 centimeters. So what we can do is take a little bit more dye and force that down into this. And then we can time, good working with partners, you can actually time how long it takes to go from that distance to this distance, how long it takes to travel the 30 centimeters. And if you can see also, since this is a confining layer here, the water's not going to travel this way, it's going to ride along this. And so this is an unconfined aquifer. What's also an unconfined aquifer is vulnerable to pollution that's at the surface because we're having a recharge in this area, so the water is traveling down into here. There's another recharge areas over here down in the tube on the simulator to fill these other areas. But you can see how this water is moving through it. And you notice that the water's traveling fairly slowly. And that's one thing about groundwater that's different from surface water. Surface water travels very quickly, relatively speaking, on the ground. But groundwater has to make its way through all these little tiny rocks and everything. So if groundwater moves a meter or so a day, that's a good distance for groundwater to be traveling. So groundwater travels fairly slowly. So we're going to also look, we can measure that in the unconfined. We can also add some dye to this confined aquifer. And again, we can measure the flow, the time it takes to move along. Here it looks like it's moving a little bit faster, but this here is a coarser grained sand, so the spaces between it are bigger. And you can see the water's already reached there, so then our time would be ended here. And so if we were taking the time, now we could measure the speed that the water is going through that aquifer. And then we can also, we're looking through the confined aquifer, we can also do it with the final bedrock aquifer. Just force some more dye down there. And now, one thing you can see, because the spaces are very big, the water travels fairly rapidly through this aquifer. Now one thing, if you can look closely, you can see that the water level, the dye water has actually come up into this area. Let me do that again, and also in this one. And these are known as flowing artesian wells. And also here you can see from the unconfined aquifer, the water is coming to the pond. And so this, again, not in the pond, but into the stream. So we can see that as this moves along, springs also feed into streams. And that's why streams can run when there's no rain. There are some streams that only run in the case of a rainfall, and a lot of the streams out west in the desert areas and all only run when it rains. But here, this stream is being spring-fed, and you can see the dye coming in. So you can see that the water traveling through the aquifer is actually feeding the stream. And up here now you can see the red rising up in this well. These are called artesian wells. Artesian wells are wells that are put down into confined aquifers. And these two particular wells are known as flowing artesian wells. And you can see that the water is rising up the well and coming out. You can see that it's red right here. The water is actually, and you can see the water coming up right there with a red color. And that's because the potentiometric surface that's from the confined aquifer, rather than calling it the the water table. We look at, we call it the potentiometric surface, and we'll look at that surface in well 2. Well 2, which is in this aquifer, and well 6 is in this aquifer. And so if we come along like that, we can see that the potentiometric surface coming along is above the ground level. So when that happens, that means the water in the well is going to rise out of the ground without need of any pump. And so you can have flowing artesian wells that are hundreds of feet down underground, and they'll spew out water at, some places hundreds of gallons a minute without any pumps. And that's due to the level of the well and where it comes out being below the potentiometric surface. So that's another thing that we can study with this aquifer, is these artesian wells. And as we saw there, the stream was fed by the groundwater from the aquifer. So we can look at also pollution, because as I mentioned, unconfined aquifers are vulnerable to pollution from the surface because it can go down. And so here we have what's known as, you'll see it's labeled as UST, that's an underground storage tank. So, and it's got a leak. So now this could be gasoline that's in there, so we can watch this plume as it moves along. Another thing that we can do while that plume's going is we can set up, we have a device so that we can set up a well to see how much water we're pumping out of a well. We can actually measure that. So I'm going to put this into well 6, into the confined aquifer. And what you're going to do is squeeze the bottle, and there's a little hole right here. And then put your finger over the hole to create suction. And now you can see that we're creating a pump and we have a well. And so we're pumping out water out of the well. And one of the things we can also see happen is you can look at when the well is pumping, there's a certain level of, there's what's known as the static level, which is the level before you stop pumping. And then there's the pumping water level, which is the level of the well when you stop pumping. So this had been up here, and now it's down here. So this is the pumping level. And so the distance between the static level and the pumping level is known as the drawdown. And so we can actually do some calculations, as there were in the lessons, to do some work with wells and looking at the well specific capacity of the well, which is the volume of water that's being pumped out per time unit, and divided by the drawdown in feet. So we can get an idea of what the specific yield of the well is. And so that's one way of measuring it. This would be like a regular municipal pumping station where it's pumping the water out to go to the community. Now here you can see this is the plume coming from the underground storage tank. And you can see that it's taken a while to move through there. And sometimes in real life, a spill or a leak from an area could take years to travel before it actually gets detected. And so sometimes you may not know that the leak has happened until a time has passed And then it gets harder and harder to try and decipher where the plume is coming from, because sometimes it'll separate. Now, one thing you'll notice is that the water from here, because this is spring fed, the water is moving into the lake and adding pollution into the lake. There's not a big flow into the lake, but as I let a little bit of water out so that it's dripping from the lake, you can start to see the red color coming through the springs into the lake. And this is how ponds and things can get polluted from leaks in area. If they're in the path, if they're in the aquifer, then the pollution can make its way into the pond. And we can see there. Now, if we had a pollution in another area, one of the techniques used for removal of pollutants is by setting a bank of wells across the plume. And so by drawing it and creating a strong suction, we can actually stop the flow of pollution. So what I'm going to do is I'm going to create a little pollution source. I'm going to take this out of here for now. And now you can see that the water level has gone back up in well 6. Up to here, it was down over here. So now that's the static, going back to the static water level. Now if we have another plume of pollutants that's coming along, what they'll do in a particular area, and we can actually see the pollution making its way past the lake along the aquifer. And now you can see how some of it's rising in there. Even though the level of the aquifer, the water table is over here, some of this water is rising. That's due to capillary action. And right at the top of the water table, there's an area called the capillary fringe. And some water will climb up, just like if you take a straw and you put it in a thin straw, put it in the water will rise a little bit in the straw. That's capillary action, which is a result of the cohesive and adhesive properties of water. Okay, now we can see that we have this pollution that's coming by this well. And I'll let it move a little bit so we can see it on the other side. So one of the ways to combat a plume is by setting up a series of wells and then getting those, and so drawing up the water. So you can see how it breaks the stream right there. Breaks the plume up. I'll do that again. So you can see how it separates this right here. And the reason for that is once you find a location where there's a major amount of pollution, and then you start pumping that up and you let the rest go, it's going to go with the groundwater, but usually it's in a lower concentration, because as a plume spreads out, it spreads out laterally, vertically, and so it becomes lower and lower in concentration. Now you can see a very good how it's rising up in the artesian well. And you can see the water level above the ground. There's a little hole in there, so that's why the water is flowing from here into the stream. And so here, what we'll do is we'll cut, with these wells, we cut the plume off, and then what they'd actually do is put the water, the cleaned water, back into the groundwater. And now you can see that what happens sometimes is that here we can still see the source. But with time, the plume could actually separate from its source once the source stops leaking. But you'll get the plume that's moving along. And so it may go miles before it might be detected in a well. And so this is one of the things, getting an understanding of why we have to protect certain areas from the potential for these areas to disturb an aquifer. Particularly, there's areas called sole aquifers. Cape Cod has a single aquifer that goes down Cape Cod. So there needs to be a protection of that, because there's areas that can result in pollution to that aquifer. And there's also zones of influence around a well. When we pump a well, what happens is it creates a cone. And this cone spreads out as we're pumping. So based on the pumping rate and where that zone of influence is, what we'll do is we'll say areas of groundwater protection, wellhead protection areas, so that as long as it's in that zone, anything coming in that zone can be sucked into the well. And it's not just, even though the water's traveling in this direction, because the well's pumping, it's going to be drawing water from both directions. So if there's pollution over here, you say, well, the water's going down that way. But based on the well, it could suck the pollution into that well. One other thing that we can also do is measure the amount of water that's flowing through an aquifer. And this is a little more consuming. We have to determine the porosity, how much water is actually in this area. And to do that, we can look at some of these soil samples. These are samples of material in the aquifer. This is the material here. Then we have some of the material up here. And then this is, this one's actually in the confined aquifer here. And this is the one in the confined, sorry. There's an unconfined layer here, which is made of this material. There's a confined area here made up of finer material. And then there's the confined aquifer made up of this coarser material. And so what we would want to determine is, based on the volume of this, we know we can calculate the volume of this cylinder and how much material we have, and then we can add water in here slowly so that it fills up. And that would determine, in this particular volume, how much water is present in that particular volume of soil. And so we can calculate the area in a certain area here, and then by knowing the volume of water in here and the speed that it's traveling, we can determine the flow of water through the aquifer. And so again, this is many exercises that we can do with this. There's also a septic tank right here that we can study the effects of a septic system. We add a little dye into there. You can see this is the leaching field right here. And one thing you want to make sure, we can adjust this so that the leaching field, the water level is lower. You want your leaching field so that it's below the water level. Right here we have the water level. And now you can see how it goes into the soil from the leaching field. But this is also an area of biological activity. And so the water is being treated by this. And then the water makes its way, you can see it's making its way over to the lake. So that's why it's important that septic systems be maintained. Because when we have the leaching of the water down there, if the water level is too high and there's not enough of a biological zone for the water to be treated, it can travel into the lake and pollute the lake or pollute a stream. So you can see I dropped the water level here, so you can see how it's passing through and moving down from the leaching field through this biological zone here where the treatment takes place, and then you have your heavy material stays in the septic system. The lighter water or the thinner water will pass out through your leaching field and then be treated. And septic systems, if they're maintained properly, can work as well, sometimes even better than a wastewater treatment plant. So it's just a matter that they have to be maintained. And make sure that these aren't getting clogged, make sure you have a proper level for the biological zone, and also that you pump your sludge out so that your sludge doesn't end up moving down into the septic system and blocking the pores that are in the leaching field tanks. And so I hope you get to come into class, into lab, and use this device, because it's a lot of fun and we can gain a lot of information from it. So have a good day and look forward to seeing you.